Imagine an AI model actively rewriting its own training code while you sleep, diagnosing its own runtime errors, and boosting its performance by 30% without a single human intervention.
I mean, it sounds like science fiction, right?
It totally does. But that is the reality of today's deep dive. Welcome to AI Paper Slop, where we summarize the latest AI and tech papers for researchers and ML engineers. We are jumping straight into the source material today.
Oh yeah, no time to waste.
Exactly. The paper is called the MiniMax M2 series, Mini Activations Unleashing Max Real-World Intelligence. So here's your rapid-fire technical summary to kick things off.
Let's hear it.
MiniMax M2 is a 229.9 billion parameter mixture of experts model. But, and this is the kicker, it only activates 9.8 billion parameters per token.
Which is just an incredibly lean active footprint.
Right. And despite that, it achieves frontier performance that rivals, GPT 5.4 and Claude Opus 4.6.
Yeah, and the secret sauce here isn't just blindly scaling up compute. I mean, anyone can throw more GPUs at a problem.
So true. It's actually this highly optimized combination of a fine-grained MOE architecture utilizing full attention.
Which we definitely need to talk about.
Oh, we will. Plus, hyper-specific agent-driven data pipelines for coding, and a novel decoupled reinforcement learning framework called Forge.
And crucially, the ability for their advanced M2.7 checkpoint to autonomously debug its own training runs. That autonomous debugging is, frankly, a staggering achievement.
It really is.
And it sets the stakes for why any ML engineer listening should care about this research. We are living in a world right now where scaling context lengths for autonomous agents is hitting severe efficiency bottlenecks.
Yeah, we're dealing with, 192K context windows?
Exactly. 192K windows packed with thousands of intermediate actions. And what the MiniMax team proves here is that you just do not need to activate hundreds of billions of parameters at every single step.
Right.
If you pair, mini activations with immaculate environment-grounded reinforcement learning, you can yield maximum real-world intelligence.
Okay, let's unpack this. Because if I'm looking at those numbers, right, 229.9 billion total parameters, but only 9.8 billion active, the routing mechanism doing the selection has to be absolutely flawless.
It really does. There's no margin for error there.
So, the flagship M2 model is a 62-layer decoder-only transformer. They use 256 fine-grained experts with only 8 active per token.
Yeah.
But what really jumped out to me in the paper is how they completely abandoned standard softmax routing. Entirely.
Right. They replaced it with sigmoid gating.
Yeah. Why make that specific architectural shift? It seems so fundamental.
Well, it fundamentally comes down to removing artificial constraints. To really get why, you have to look at the mathematics of softmax.
Okay, break it down.
Softmax enforces a probability distribution that must always sum exactly to 1, right? So it is inherently competitive.
Oh, I see where you're going with this.
Yeah. If you have a token that represents a really highly complex concept, say a super nuanced piece of C++ memory management,
Sure.
and 3 different experts contain critical, highly relevant knowledge for that one token, softmax forces them to basically fight for a share of that one probability.
Okay. So softmax routing is basically like slicing a single pie. If one expert gets a huge slice because it's highly relevant, the other experts are forced to get a smaller slice.
Right.
Even if their knowledge is also perfectly applicable to the token.
Exactly. But sigmoid gating is entirely different. It's like an independent grading rubric.
Oh, I like that.
Yeah, every single expert is evaluated entirely on its own merit. Every expert can score an A if they are highly confident. It completely removes that zero-sum competition from the routing.
Wow. So multiple experts can activate simultaneously with really high confidence.
Precisely. Which leads to much smoother, more stable training dynamics overall. But the researchers had to go a step further to manage the system.
Because if everyone can get an A, you might get great inflation, right?
Exactly. With sigmoid gating, you risk all the experts just firing all the time if they get overly confident. So to prevent that, they introduced learnable per expert bias terms.
Wait, so these are just scalar values added to the routing scores before the sigmoid function is even applied?
Yes. They are routing score shifts optimized directly alongside the model parameters during backpropagation.
Oh, interesting.
They act as an implicit regulator for expert utilization. So over time, the model naturally learns to penalize overused experts and, boost the underused ones.
That is so elegant. And because of these bias terms, MiniMax was able to drastically reduce their reliance on auxiliary load balancing losses.
which is huge. Historically, those auxiliary losses can aggressively interfere with the primary language modeling objective.
Right, causing the model to prioritize perfectly balanced routing over actually predicting the next token correctly.
Exactly. It's a classic case of Goodhart's law in machine learning.
So, okay, we have this incredibly efficient routing foundation, which makes sense because the whole philosophy is mini activations. But then I read the section on their attention mechanism, and it feels like a glaring contradiction.
Oh, the GQA stuff.
Yeah. They stuck with computationally expensive, full multi-head attention, specifically grouped query attention, or GQA. They completely bypassed all the trendy, hyper-efficient linear attention or hybrid attention models. I just don't get it.
It seems backwards at first glance, I know.
Why prioritize efficiency in the feed-forward layers, but just accept the immense compute cost of full attention?
It really comes down to a hard lesson in real-world evaluation versus proxy metrics. The paper actually details these extensive pre-training experiments they ran with hybrid sliding window attention, or SWA.
Okay, for context for the listeners, sliding window attention restricts a token so it can only attend to a fixed number of recent tokens, say the last 4,000 tokens.
Right, rather than the entire historical context. It's incredibly memory efficient. And what they found is a crucial warning for anyone building agentic models right now.
What happened?
Well, when they ran hybrid SWA on standard short context benchmarks, it performed beautifully. Like, it matched full attention almost perfectly.
But autonomous agents aren't writing haikus. They don't operate in short context.
Exactly. And that is where the architecture completely broke down. Past the 32K context mark, hybrid SWA catastrophically failed at multi-hop reasoning and long context retrieval.
Oh, wow. Catastrophically.
Yeah. Think about the mechanics of an agent doing deep search or navigating a massive software repository. The model might read a variable declaration, right?
Right.
Then it reads 50,000 tokens of other files, and then it needs to recall that exact variable to write a new function.
Oh, I see. And with SWA, that variable has fallen out of the attention window.
Exactly. The model literally cannot see it anymore. Because agentic tasks demand these ultra-long, highly dependent horizons, MiniMax decided that the attention coverage limitations of hybrid SWA were just simply unacceptable.
So full attention was non-negotiable for real-world deployment.
That's the conclusion they reached.
I hear that, but I have to push back here. With a 192K context window, full grouped query attention is an immense bottleneck for training throughput.
Oh, it's massive.
The memory constraints alone are staggering. How do they realistically compute this during reinforcement learning rollouts without just constantly running out of GPU memory?
It is a severe challenge. They solve the overarching memory and throughput issues through some brilliant system-level infrastructure, which we will dive into with the Forge system shortly.
Okay, good, because I was stressed just thinking about the CUDA out-of-memory errors.
Right. But to partially address the efficiency demands right at the architectural level, they incorporated a multi-token prediction module, or MTP.
Okay, I want to make sure I understand this clearly. Instead of the standard paradigm where the model just predicts the next single token, it's trained to predict the next K tokens simultaneously.
Yep.
The paper mentions they start pre-training with K equals 1, but during the decay phase of continued pre-training, they expand it to K equals 3.
Right, which supports multi-step speculative decoding at inference time.
Yes. For those unfamiliar, speculative decoding is where you have a smaller, faster model, in this case the MTP modules, acting almost like an intern.
That's a great way to put it.
It quickly drafts a guess of the next 3 tokens.
Mm.
Then, the massive main model, the senior engineer, evaluates those 3 draft tokens and verifies them in a single forward pass.
Right. And if they are correct, you just generated 3 tokens for the compute cost of 1, which yields a substantial throughput bump.
But the really clever part is how MiniMax implements this expansion from 1 to 3 modules, isn't it?
Yeah, what's fascinating here is that they don't just randomly initialize the new neural network weights for those modules.
Right, they use weight copying from the main model. Why is that distinction so important?
It's all about the underlying training dynamics of that transition. If you randomly initialize new modules deep into a training run, you introduce a highly volatile loss spike.
Because they're basically just outputting noise at first.
Exactly. The gradients flowing backward from those untrained, garbage-producing modules will temporarily corrupt the carefully learned, really delicate representations of the main model.
Oh, that makes sense.
By initializing the new MTP modules via weight copying, those modules start their life with a deep, sophisticated understanding of the language distribution. So they converge significantly faster, and it almost entirely minimizes any disruption to the main model's stability.
Okay, Okay, so we have this fast, efficient, stable base model. But pre-training just teaches a model to predict the next word. If I asked this base model to build a functional React application right now, it would fail.
Completely fail.
Because it doesn't know how to use a compiler or navigate a terminal. How do they bridge that gap?
Well, we have to look at how they taught this model to interact with the real world through their agent-driven data pipelines, starting with SWE scaling for software engineering.
Let's get into it.
This is where the methodology gets incredibly rigorous. They knew they needed high-quality coding data, but raw GitHub pull requests are notoriously noisy.
Oh yeah, they are full of incomplete thoughts, broken builds, bad code.
Exactly. You cannot just scrape them and train a frontier model. So to solve this, MiniMax built a system where an agent autonomously constructs runnable Docker environments for tens of thousands of real PRs.
Wow.
And for bug fixes, they specifically extract F2P and P2P test cases.
Wait, break those acronyms down for me.
Sure. So F2P stands for fail to pass. The agent acts in a sandbox, attempting to edit the code to fix the bug. If the previously failing test now passes, the model gets an objective signal that its code works.
Okay, that makes sense. And PDP?
PDP stands for pass to pass. This is arguably even more important. It runs all the tests that were already passing before the fix.
To ensure the model didn't introduce a regression bug while solving the primary issue.
Exactly. Only trajectories that satisfy both are added to the training set.
That makes perfect sense for modifying existing code where you have predefined tests. But what about building something entirely from scratch?
That's where application development comes in.
Right. They use a framework called Agent as a Verifier, or AAV. And reading through this section, it's clearly not just a simple static code linter checking for syntax errors.
Not at all. It is a hierarchical verification system operating across 3 distinct layers.
Let's hear them.
First is the execution layer. Basically, does the code actually build? Are there fatal JavaScript errors the moment the page loads? If it fails here, the trajectory is instantly rejected.
Brutal, but necessary.
Second is the interaction layer. They use a web testing framework called Playwright to instantiate an agent that literally navigates the deployed application.
Wait, really? Like a user?
Yeah. It clicks the buttons, fills out the text forms, and verifies that the state of the application changes correctly based on those actions.
That is wild. And the third layer?
The third is the visual aesthetics layer, evaluating the UI layout against design standards.
So what does this all mean? The agent as a verifier is essentially a synthetic QA engineer.
That's exactly what it is.
It's actively poking at a deployed website to see if the submit button actually fires a database request before it allows that specific coding trajectory into the RL training data. It's doing the grueling testing work human developers hate doing.
Absolutely. And they do something very similar for command line tasks with their terminal gem pipeline.
Oh, right, where they convert raw Stack Overflow posts into verifiable terminal tasks.
Yep. And they dynamically strip away the explicit hints in the prompt to slowly evolve the query difficulty.
So all of these pipelines generate an incredible volume of high-quality, multi-step agent data. But this introduces a crippling systems engineering problem, doesn't it?
The impossible triangle.
Right. In traditional reinforcement learning, you need a really tight loop. The model takes an action, the environment returns a reward, and you compute the policy gradients to update the model weights.
Right.
But if you are running RL on an agent task that takes 2 hours of wall clock time to execute, like building and testing a Docker container, your GPU cluster is just in there, stalled, waiting for the reward.
Or, even worse, the model weights have updated so many times in the background that by the time the 2-hour task finishes, the policy gradients are completely stale.
Exactly. So to solve this impossible triangle of system throughput, training stability, and agent flexibility, the paper introduces the Forge RL system.
The central breakthrough of Forge is decoupling. It entirely separates the agent side, meaning the system's producing the trajectories and interacting with the environments from the training and inference side.
How do they talk to each other then?
They bridge these two worlds with the middleware data pool. The agent side doesn't know or care about backpropagation or policy gradients. It just runs the sandboxes, manages the context memory, and drops the state action observation tuples into the data pool.
So it supports multiple types of architecture seamlessly. The paper mentions it handles both white box agents, where the internal context management logic is exposed directly to the framework, and black box agents, which might just be interacting via a rigid API.
If we connect this to the bigger picture, this decoupling is the holy grail for ML engineering teams.
Really? The Holy Grail?
Oh, yeah. It means your researchers can iterate on incredibly complex multi-agent scaffolds, like adding hierarchical subagents, dynamic context rewriting, or new tool use loops, without ever having to touch the core RL training code.
Because the training engine just asynchronously pulls data from the middleware pool and computes the gradients.
Exactly.
I love the modularity of that, but surely that creates an absolute scheduling nightmare. I mean, you have extreme variance in agent rollout times.
Oh, absolutely.
Some simple API calls take 3 seconds, while a deep reasoning chain compiling code takes an hour. If the training scheduler pulls from the data pool using strict FIFO first in, first out, don't you get severe head-of-line blocking?
You do.
Like, one slow 1-hour task stalls the entire cluster from training on the thousands of quick tasks sitting behind it.
Exactly. Strict FIFO optimizes for perfect data distribution, but completely ruins throughput. But the alternative is just as bad.
You mean greedy scheduling?
Yeah, if you use greedy scheduling, meaning the scheduler just grabs whatever task finishes first, you introduce severe bias.
Let me guess. Early in the training batch, the pool is flooded with short, easy tasks that finished quickly.
Right.
So the model trains heavily on those. Then later in the batch, all the 2-hour complex tasks finally finish, and the model trains exclusively on hard tasks.
Exactly. And that kind of gradient oscillation would completely ruin your training stability.
So how does Forge fix it?
The Forge system implements windowed FIFO scheduling. They define a sliding window over the generation queue, for instance, 30% of the total queue size.
Okay.
Inside that specific window, the scheduler is allowed to fetch greedily. Any completed task within that 30% block is instantly pulled for training, which keeps GPU utilization extremely high.
But what about the boundaries?
Right. Across the window boundaries, strict ordering is enforced. The window simply cannot advance forward until the oldest tasks at the very head of the queue are completed.
Oh, that is so smart. It is a brilliant mathematical interpolation between maximizing throughput and preserving the true distribution of the training data.
It really is.
Okay, so Forge solves the temporal bottleneck, but we still have a spatial bottleneck. Even with perfect scheduling, the sheer volume of tokens in these multi-turn conversations is crushing.
Going back to that 192K context window.
Right. In a multi-turn agent trajectory, the system prompt, the tool descriptions, and the early conversation history are repeated constantly with every single new action the model takes. How does M2 solve that staggering token redundancy problem?
They solve it through a mechanism called prefix tree merging. Think about a standard training batch. If you have multiple different completions or actions branching from the same initial rollout, they all share a substantial common prefix.
Yeah.
Traditional causal language modeling treats every single one of those samples independently, meaning the GPUs are redundantly recomputing the exact same attention keys and values for that shared prefix over and over again.
Which is just a tragic waste of compute when you're dealing with hundreds of thousands of tokens.
Exactly. Forge solves this by algorithmically merging sequences that share a prefix into a unified tree structure. During the forward passive training, that shared prefix is computed exactly once.
Just one?
Yes. The computation then dynamically branches out into the individual response segments. After the forward pass is complete, the tree is deconstructed back into independent samples to compute the final loss.
Oh, that makes total sense. It's exactly like saving a video game right before a boss fight.
That is a perfect analogy.
Right. Instead of replaying the entire 2-hour level every single time you want to try a new strategy, which is essentially recomputing the context prefix, you just branch off from the save point.
Exactly. And because causal attention over a shared prefix is mathematically identical regardless of how it branches in the future, this yields up to a 40x training speedup with absolutely zero approximation error.
Wow. So it is a completely lossless optimization.
It is. And that profound efficiency unlocks another critical feature, interleaved thinking.
What's that?
Well, many frontier models today hide or intentionally drop their chain of thought reasoning between agentic turns simply to save context space. MiniMax M2 does the exact opposite. It appends all of its thinking blocks directly to the persistent message history.
Why is that persistence so important? Doesn't that just bloat the context even more?
It does, but it prevents state drift. By keeping the thoughts, it creates a persistent plan, act, reflect loop.
Plan, act, reflect.
Okay, the model forms a plan, calls a tool, observes the result, and reflects. Because its previous thinking is still entirely visible in the context, it can actually reuse its own hypotheses.
Oh, So if a tool fails, it doesn't have to redundantly rederive why it chose that tool 3 steps ago.
Exactly. It just reads its past logic and pivots.
Here's where it gets really interesting. When you combine the mini-activation architecture, the intense agentic data pipelines, the decoupled Forge RL system, and this persistent interleaved thinking, you arrive at the paper's most provocative result.
The self-evolution.
Yes, a model that can actively engineer itself. They took the advanced M2.7 checkpoint and evaluated it on OpenAI's MLE Benchlight.
Which is a benchmark specifically designed for autonomous machine learning engineering.
Right. M2.7 achieved a 66.6% medal rate, tying Google's Gemini 3.1 Pro.
Which is impressive, but the score isn't even the crazy part.
No, it's how MiniMax is using this model internally with their model iteration system.
Yeah, the operating principle of that system is human steer, but M2.7 builds.
Right. The human researchers configure the high-level goals, but the agent operates within a harness generated entirely by M2.7 with zero human-written code.
Zero. M2.7 actively profiles ongoing RL training runs. It reads the raw server logs, diagnoses metric anomalies, and directly modifies its own agent scaffold across a 100-round autonomous iteration cycle.
I want to make sure the gravity of that lands for everyone listening. It is analyzing its own failures and editing its own code to fix them.
Yeah, it's wild.
The paper highlights a specific case where M2.7 was analyzing training logs, discovered a better parameter combination for its generation scripts, and proactively implemented a loop detection mechanism for its tool calls.
And the result of that?
That single autonomous intervention yielded a 30% performance gain on their in-house evaluations. This model is actively taking on the day-to-day grueling debugging workload of the very ML engineers reading this paper.
The researchers explicitly note it is absorbing up to 50% of the daily iteration workload for their RL team. It is an extraordinary leap in self-improving systems.
Let's summarize the core triumph of this research before we go. The MiniMax M2 series proves unequivocally that you do not need to activate hundreds of billions of parameters per token to reach the absolute frontier of AI performance.
You really don't.
By committing to full attention where long-horizon reasoning demands it, building strictly verifiable agentic data pipelines to ground the model in reality, and engineering the Forge RL system to handle the immense variance of agent rollouts.
Right.
They have squeezed maximum real-world intelligence out of a 9.8 billion active parameter footprint.
And that leads to a final thought I want you to mull over. M2.7 is already autonomously debugging its own RL infrastructure and rewriting its own execution code.
Right.
If a model can effectively and iteratively improve the very scaffold that trains it, at what point does the bottleneck in frontier AI development shift entirely away from human engineering ingenuity and purely into the realm of raw, unsupervised compute for self-play?
That is a staggering thought to end on. Thank you for joining us for this deep dive into the source material on AI Paper Slop. We will see you next time.